Hello, thank you for joining my presentation. In this talk, I'll be presenting our work on fabricating reliable, robust, and substrate-independent antennas on textiles for wearable e-textile applications. In this talk, I'll cover the fabrication details, the reliability methods, and reliability testing, and also potential applications in terms of different microwave devices and antennas. The main challenge we're looking at is a lot of opportunities with e-textiles, a lot of opportunities to wearables, but there are two fundamental challenges. The first is reliability. How can we make these devices last longer, and how can we make them withstand the harsh rigors of day-to-day use? And also, when we fabricate them, how do we overcome the fundamental limit, and that is the roughness of substrates, the variety of textiles, the variety of the composition of how we fabricate them and how we print on them. It's needless to say that there are lots and lots of applications of antennas in wearable communications, from body-centric communications, in-body, off-body, and even between on-body nodes, and there are a variety of implementations that address these requirements. These requirements extend to the millimeter wave region, and we have seen applications all the way up to 60 gigahertz reported as early as 2013. And we've also seen innovative topologies that go to transfer information and power simultaneously, which we have recently reported. And in many of these cases, we rely on specific fabrics, such as felt, which has got high thickness, but it's also very rough, and it's very unfriendly for printing and for direct treatment. And textiles more generally require surface treatment. So for example, before you can inkjet print, dispenser print, or screen print directly on them, you have to treat the surface to overcome the roughness. So you can see in a scanning electron micrograph, or an SCM micrograph on the bottom of my slide, the textile substrate itself is very rough, and before the antenna can be printed on the surface, a screen printed interface material is required in order to reduce the roughness and reduce the amount of conductive ink which is required. Otherwise, textile antennas will become extremely expensive, especially given the large area a microstrip patch or a ground plane would require. So what we really need is a substrate-independent method to realize antennas, not only to fabricate them, but also to make them more reliable and to enable them to maintain the RF performance regardless of the textile substrates they are being printed on. So in this work, we take the classic antenna design for wearables, which is a microstrip patch. It generates a broadside radiation pattern of the body in its first order mode. So it's ideal for off-body communication. It offers lower SCR, low detuning, and it's simply the most widely chosen antenna design for wearable applications. We designed it for the 2.4 gigahertz band just because that's where most of the wearable applications are, from communication to power transmission. And in order to implement it on a multi-layer textile substrate, we use a proximity-coupled feed without any through textile wires or inductive probes in order to reduce the complexity of the approach and also to make it more robust and easy to fabricate. So the main aspect of this work is being able to screen print an antenna. Screen printing is an extremely scalable fabrication method, and to be able to do that on different textile substrates regarding of how rough they are. Felt is one substrate you'll notice in most of the antennas literature because it's quite thick and it also has a relatively low dielectric loss tangent, so it will improve the radiation efficiency of the antenna. However, felt and other non-woven fabrics are very, very rough, so the measured surface roughness can be over 200 to 300 micrometers, and that is unsuitable for direct printing. What we do in our work is, instead of printing on the fabric, we print on an interface layer or on a transfer layer, that is in this case a polyurethane film. So as you can see in figure A, we print directly our conductive silver ink, which is a low temperature ink, on our polyurethane film, and then we cure it at 80 degrees for more than 10 minutes in the oven, and that's called the pre-curing stage, where the silver is now ready to be placed directly onto the textile fabric, and then, as you can see in figure D, heat pressed onto any textile substrate regardless of how rough or how non-uniform it is. And as you can see in photograph E, we can also use this method for multi-layered integration, which in the end of the presentation, you'll see a potential application of it. So what does the structure look like? In here we have a microstrip line, which in fact has got a capacitive overlap in the center. And you can see that even with manual alignment, the line maintains a good resolution. You can clearly see in the micrograph and even in the optical micrograph before we move to the SEM that the surface is very rough, and this roughness has translated to the silver layer. However, we are still able to maintain a uniform impedance controlled microstrip line on this very rough substrate where direct printing would have otherwise been impossible. If you look at the SEM, you can see that the fabric is extremely rough and that the polyurethane interface has bonded with the fabric itself, and then it allows us to print our silver layer and even deposit a second interface layer and print more layers to enable multi-layered RF circuits on fabrics. So looking more at the fabrication method, the thin polyurethane layer is breathable, it's very flexible, it does not change the feel of the substrate below it. And combining the polyurethane and the silver thickness, we're still looking at less than 0.1 millimeter added thickness to the fabric, which is less than conductive electric plated textiles. And the shear resistance is still comparable, and it's less than 0.5 ohms per square if the silver is treated properly and if it is cured at the right temperature and for the right amount of time. So moving on to the characterization of the antenna, there are two things. There is the input bandwidth, there is reflection coefficient, and then there's the far field properties. And we've characterized both experimentally, and we've characterized both after bending in order to assess the antenna's reliability. First thing we perform, as usual, is the S11 measurement, and we've measured the antenna when it's flat before any external tests. We've measured it on body with bending, and also measured it after repeated bending to mimic the real world use. The way we did that is we've subjected the antenna to more than 10,000 automated bending cycles, and for this we have chosen the sharpest radius of 5 millimeter, which matches bending during washing as well as crumpling, and will give us an accurate estimate of bending over the lifetime of a typical e-textile antenna. And as you can see in the S11, the bending rate after 10,000 bending cycle over the 5 millimeter radius, the antenna still maintains its 100 megahertz bandwidth. It still maintains pretty much the same S11 response. It has drifted slightly, but this could be mostly due to measurement error and perhaps misalignment between the layers and the feed, which does affect the input impedance of the antenna after all. But it still maintains its bandwidth. In fact, it has got broader bandwidth, so it shows that the antenna after 10,000 bending cycles, which is significantly a higher number than most of the tests you see reported in antenna literature, it can still maintain its bandwidth with a very good S11 response. Moving on to what really matters, which is the far field properties. So we report for the first time radiation pattern measurements before and after bending, as well as realized gain measurements before and after bending. We perform our measurement in an indoor lab environment without an anechoic range, which would explain some of the variation you see around the side lobes and the fact that radiation nulls are inconsistent. However, if you look at the main lobe, the simulated values, the pre-bending and the post-bending values are pretty much in perfect agreement. And the more important thing is that when we measure the gain using a two antenna method in the far field, we got the same realized gain within 0.5 dB measurement error, which would exist in most antenna measurement ranges. And you can find more about that in our proceedings paper and the exact gain and radiation efficiency values, which are higher than 50%. The 3D radiation patterns are also consistent, so you can see that before and after bending, the pattern drifts slightly. You can see that the main lobe has got a bit of shifting over 3D. However, the antenna's broadside radiation is still maintained. It still radiates off body, and as we just mentioned with the gain values, the total efficiency is more or less the same, which is what you would expect, and what it implies that the effector traces have not degraded, which is also backed by our DC measurements, where the DC resistance measured using a precision impedance analyzer did not increase at all across the patch, and the Microstrip feed, which shows that it's a highly reliable design and a highly reliable fabrication method. What can we do this for? We can use it not just for antennas, but also for more complex, much higher frequency microwave and millimeter wave passive RF components. So we have taken these to print microstrip capacitors. We've used the method of multi-layer integration to realize embedded concealed capacitors in a microstrip line for DC blocking applications, which you would expect to see in antenna feeds. And we've characterized its transmission characteristics all the way up to 50 gigahertz, and for two different textile fabrics, polycotton, a relatively smooth fabric that's quite lossy, and also felt, which is a lower loss and significantly thicker and rougher fabric. And we see for both that the attenuation is less than 0.5 dB per millimeter, all the way up to 50 gigahertz, so that's 5G compatibility. And its attenuation is also comparable to transmission lines implemented in low loss polymers like liquid crystal polymer, LCP, and polyamide and Captain, which shows that textiles, even though they are lossy, they are very rough. With this fabrication method, they can support millimeter wave applications up to 50 gigahertz. And in our DC blocking lines, this is the highest frequency application of a printed RF component to date. So it shows that the fabrication method is not only suitable, it's not just reliable, but it works all the way into the millimeter wave spectrum with comparable losses to significantly more expensive and more complex fabrication methods. So to summarize my talk and some other contributions, screen printing is not limited to smooth surfaces. It can be done on rough textiles. It can be done on different textile substrates using transfer printing. Polyurethane films can be used for transferring and encapsulating antennas, making them more reliable, making them more resilient to bending and also to washing and potentially waterproofing them. We characterize this through the radiation patterns and the S11, and both of them have shown a very stable and bending resilient response. And we've also shown that this fabrication technique is not limited to antennas, it's not limited to the UHF spectrum and relatively large area components like microstrip patches, but we can also fabricate precise RF and millimeter wave components such as passives, capacitors, and DC blocking lines, which represents the highest frequency reported to date and over 10 times improvement in frequency of operation over previous printed components. So thank you for listening, and I look forward to getting your questions and hearing your feedback. Thank you.